In this lecture, I'd like to talk about the concept of electron configuration. But before we get into that, it's really important to talk about the following principle known as the Aufbau principle. Now, this principle will help us explain electron configuration. Now, what this principle states is the following. Whenever an atom adds a new proton to create a new element, it must also add another electron to neutralize that extra charge that comes from that extra proton. So, the problem is the following. Whenever we add a proton, we know exactly where our proton goes. That proton goes into the nucleus along with all the other protons. What about our electrons? We have options as to where to place those electrons because we have many different shells, we have many different subshells, and we have many different orbitals within our subshells. So luckily, nature always tends to form the lowest possible energy state. Therefore, whenever we add electrons to our atom, that electron will go into the lowest possible subshell, lowest possible energy subshell. So let's examine the following concept, and I state the following. As electrons move further from the nucleus, our energy level will increase, and this is true. Now let's examine why it's true. Well, let's look at the following illustration. Suppose we have a proton in our nucleus, and this is an electron a distance r away from it. Now, Coulomb's law will give us some force that this guy feels due to this electron, and then it will also give us the same force except in negative direction that this guy feels due to this proton. Now, my question is, how do we get this electron not a distance r away, but a distance 2r away? In other words, how do we move this electron from this guy, from this distance, to this distance? Well, remember, if this is a positive force and this is a negative force, these guys are attracting. They want to come close. So in order for me to move this guy a distance r here, a distance 2r from our nucleus, that means I have to do work on that electron. So if we consider our proton and our electron a system, that means I have to do work on my system to move this electron a distance r away from this electron, right? So that means work must be done on our system, and because work is a transfer of energy, energy must be transferred into our system. So our overall energy of our system increases as the electron moves away from our nucleus. And that's exactly why placing electrons further away from our nucleus will increase the energy of our system. And that's exactly why nature tends to place electrons as close to our atom, as close to our nucleus as possible, because placing it further away increases the energy of our system, and nature tends to take the lowest energy state. So that's exactly why when we look at the principal quantum numbers, as our principal quantum numbers increase, as we go from n equals 1 to n equals 2 to n equals 3, or from orbital s, p to d, our energy will increase as we go down this table. So now let's talk about electron configuration. Electron configuration is simply a systematic approach to representing and showing exactly where our electrons are placed within any given atom. In other words, in which shells or in which subshells are our electrons found. So let's look at the simplest atom, the H atom. The H atom has one proton and one electron. The proton is the nucleus, the electron is found orbiting our nucleus. Now, what are the quantum numbers of this electron? Well, this guy has the first principal level, the first principal quantum number, or n equals 1. And that means if n equals 1, our second quantum number, our L, must be 0. And if L is 0, that means our third quantum number, the orbital in which our electron is located, is the s orbital. So, to represent this in an electron configuration way, we simply do the following. We put a coefficient in front of our s. So the 1 represents our shell, our principal quantum number. Our s represents our subshell. And at the same time, it also represents our orbital in which our electron is in. The superscript, the 1, represents the number of electrons. So we have 1 electron, so we have a superscript of 1. So this is the electron configuration for this atom, for the H atom. Now, any atom or any element on the periodic table has an electron configuration. So let's look at another one. Let's look at oxygen. Oxygen has an atomic number of 8, and that means in its neutral state it has 8 electrons. So let's look at its electron configuration. Now notice that n equals 1, it could fit 2 electrons, because when n equals 1, our L equals 0, and we only have 1 orbital, the s orbital. So we can place a maximum of 2 electrons into any orbital, so we can place 2 electrons into shell level n equals 1. How about n equals 2? Well, n equals 2 has a maximum of 2 to the 2, so maximum of 4 orbitals. That means if we have 4 orbitals, I have an s orbital and 3 p orbitals, right? So I could put a maximum of 8 electrons into my n equals 2 energy level, into my n equals 2 shell. So I place 2 electrons into my s orbital. This guy's my s orbital, and then I could put 6 electrons into my 3p orbitals. So 1, 2, 3, 4. I put 4 because I only have 4 left over. So now let's look at the electron configuration for our oxygen. In our principal quantum number 1, n equals 1, we have only the s orbital. So we place 2 electrons here. So 1s2. And now n equals 2, we have an s and the 3 p's. And that means we first place 2 electrons into our s, so 2s2, and then we distribute electrons into our p's. And we have 3 p's. So we start by putting 1 in each, and I'll explain in a little bit why we put 1 here, 1 here, 1 here, and then 1 here, and not 2 here and 2 here and none here. I'll explain why in a second. Now, so I place 1 here, 1 here, 1 here, and then I place my 4th one into my x. So we can also represent this guy in the following way. We simply erase all these x's and z's, and simply say 2p, and we place a 4 on top. Now, whenever we do this, we make the assumption that you understand the fact that this is not a single orbital, but this is actually 3 orbitals. Because if this was a single orbital, the 4 would not make sense, because you could only place a maximum of 2 electrons into any orbital according to the Pauli exclusion principle. So that's the electron configuration: 1s2, 2s2, 2p, 2p4. Since oxygen has a maximum of 8 electrons, that means 2 plus 2 plus 4, 8 electrons, so this makes sense. So every atom on the table, every element, has its own electron configuration. Now, let's look at sodium. Sodium has the following electron configuration, right? It has 11 electrons in its neutral state. How about neon? Neon has 10 electrons. It has a perfect configuration. Every single orbital is completely filled. And remember, every atom on the table wants to become a noble gas. So every atom wants to become, or wants to take the electron configuration of a noble gas. And neon is in fact a noble gas. Another way of representing electron configurations are using noble gas configurations. Notice that 1s2, 2s2, and 2p6 is identical to 1s2, 2s2, and 2p6 of neon. So we can replace this whole guy simply with neon. And these brackets simply mean the electron configuration of neon, and then we add this guy, 3s1, and this means this is the electron configuration of our sodium, right? Because sodium has 1 more electron than neon. That electron goes into the 3s1 energy level. Now, the ground state of any atom represents its lowest energy state. This is the ground state of sodium. This is the ground state of hydrogen. And this is the ground state of oxygen. Now, when atoms go from a ground state to an excited state, what that means is they form ions. or they form excited state atoms. And that simply means electrons jump to a higher state. And we'll talk more about that when we'll talk about the photoelectric effect. So one important aspect of electron configuration must be understood. Electron configuration doesn't necessarily have to order things from lowest energy to highest energy. Although that's usually the case, that doesn't have to happen. In other words, let's look at the following important facts. So 4s, that energy level is at a lower energy than 3d. And 5s is at a lower energy level than 4d. And this holds for 6s and 5d as well. Now these things you just have to simply remember. Now if we look at the electron configuration for bromine, which has 35 protons and 35 electrons, we see the following electron configuration. Now this guy makes sense because 1s comes before 2s, and 2s comes before 2p, and 2p comes before 3s, and 3s comes before 3p. In other words, this goes from lowest energy level to highest energy level. And since we just said that 4s is at a lower energy level than 3d, it would make sense to place the 4s2 before the 3d10. And this would be the correct electron configuration if you're actually ordering from lowest energy level to highest energy level. But this doesn't have to be the case. In other words, if I flip these guys, that isn't wrong. That's allowed. That's allowed to happen. And that's because electron configuration doesn't necessitate that you have to order them from lowest energy to highest energy. Although if in a question it asks you for the proper electron configuration that order things from lowest to highest, then that has to happen. Then this is the proper electron configuration. So ions also can be represented using electron configuration. For example, let's look at sodium plus. It has 11 protons and 10 electrons. So in order to write the electron configuration for this guy, we simply take away one electron from the highest energy level. So in this case, it would be 1s2, 2s2, 2p6, and we took out one electron from the 3s1 orbital, so that guy disappeared. Now if we make this guy into an ion, right? Let's say we make it into Br plus ion. We take one electron away. That means we take it away from the highest energy level. That means we take it away from 4p. If we want to add one electron and make this into an anion, Br negative, we add an electron. And we add the electron to the highest energy level, 4p5. So this guy gets 4p6 if this guy is Br minus.